Hello and good afternoon to all of you. Thank you for joining this session, and especially a special thanks to all the organizers of this conference for giving me the opportunity to be here today. My name is Michele Fusero, and I'm a Research and Development Engineer at Hitachi EBB Power Grids, and I work as a control specialist for battery energy storage systems in Grid Edge Solutions product group. Our R&D core team is based in Genoa, and that's exactly where I'm speaking from now. I'm very glad to be here today for this session, and the focus of the session will be on hardware-in-the-loop testing and the way we apply it in order to strengthen our image solution. And as anticipated, I'm not going to be the only presenter of this session because there will be a second part held by Henrique on the topic of HIL automated testing. Okay, we can start, and let's start with something that all of you attending this conference know very well, and that is that our energy ecosystem is continuously evolving. The most significant change that has happened is so far is at the interface between the consumers and the grid, and this was especially thanks to the increased penetration of distributed energy resources, making the profile of the consumers change from a static profile to a dynamic one. And now grid operators have to respond to this new complex and distributed network with the introduction of which introduces bidirectional power and information flows, and they need digital solutions for this. So Grid Edge Solutions is one of the product groups of Hitachi EBB Power Grids, and is leading the energy innovation and transition. And our portfolio includes battery energy storage systems and digital automation solutions for the energy optimization management, for advanced control and monitoring. We will see that a bit better in the next slides. So ours is a vertically integrated solution where power is the foundation. And in the power block, we have the Image Power Store, which is a plug-and-play smart battery energy storage system that well fits to grid-connected applications, thanks to the already certified compliance with many of the grid codes for several countries and the continuous integration of new grid code with compliance, and also fits well for a very weak system or islanded system, thanks to the grid forming capabilities that it has. We then have the automation part with the image control, which is a power management solution that can operate with any type of DER and providing distributed or centralized controls. The image SCADA and DMS are the other components of the automation block, and they are solutions for plant automation and energy management on premises. And then we have the digital part, and there the digital is the part that is introducing new services through the Internet of Things technologies, and is mainly made of the image monitor, which is a cloud solution for remote monitoring and control of and optimization of any asset's performance, and the image applications, which are solutions of software as a service, and that can forecast production, optimize the planning, improve productivity and economic gains. Our products fit to multiple applications. Some examples are utilities and service providers, which are striving to effectively manage their increased portfolio of distributed energy resources. Or they can be commercial and industrial sites, which are aiming to unlock new economic opportunities, or island and remote communities, which are seeking for energy autonomy. Whichever is the application, our common target is always to be able to maximize the integration of renewable energy sources, to increase the operation and reliability and resilience of the system, to lower the CO2 emissions and reduce the energy costs. So as I anticipated, this session will be focused on hardware-in-the-loop testing. So testing is the most powerful solution that we have in order to guarantee that our image products are robust, reliable, and efficient. And nowadays we have several possibilities, we have a rich availability of testing solutions. And all of them differ mainly in the ratio, I would say, between simulated virtual components and the real components. So we can have fully simulated test systems where all components are modeled through an equivalent representation. Or we can have test systems where we have a mix of simulated components and real components. Or more, we can have real test systems in which there is no simulated components, but only real ones. From our perspective, the key differentiators between all these types of testing are the coverage that we can achieve with the selected test platform, the fidelity of the test platform, and the overall cost of the solution. So generally, we have that the higher is the portion of simulated components, and the higher will be the test coverage. But also, we can get a reduced fidelity of this test, and therefore, it's always hard to find a good balance. Let's say that replacing a component with its virtual model brings two approximations, but also it minimizes or avoids the risk of damaging costly components during a test. Therefore, it allows for a higher test coverage, which is further increased by the possibility of easily scale up a test setup in order to represent larger systems. Then the cost of the test solution is dependent typically on the amount of power and control components that we include in the test, the amount of real power and control components that we include in the test setup. Therefore, it is lower for a simulated system, and as we've represented in the colors in this plot. So controller and power hardware in the loop are the ones that are providing an optimal balance between all these factors. And they allow us to combine real and simulated components in a way that is specifically designed depending on the target of our test. And still, they provide us with a good test coverage and fidelity, and with a cost that can be low or moderate. These are the main reasons why hardware-in-the-loop testing has become a pillar in our product development, and we'll now see how we apply that to our development. So the unit testing is our system application of the is our simplest application of the hardware-in-the-loop technology. We use this method very extensively in order to validate our image power store. As I said earlier, the image power store is our battery energy storage solution, and it is required to operate in both grid-tied configuration, but also off-grid. Therefore, we need to test it in both conditions, and also we have to make sure that the transitions between these conditions can be done in an optimal way. So despite its simplicity, this test setup allows us to validate, first of all, any algorithm that we develop during our daily work. Indeed, the final stage of our development always goes through a hardware-in-the-loop testing session, so that we can not only validate the quality of the function we have developed, but also how it runs on the selected controller. We can also assess the performance of our final product in terms of speed of response, stability of the control, possibility to write through events in the grid. And last, we can verify the compliance of our product against specific customers or grid code requirements. And an example of this is that we have used the hardware-in-the-loop testing as a pre-assessment before starting the real testing for the grid code compliance of our power store against several of the grid codes, especially in Europe. With this method, we have been able to already address any possible issue we have uncovered during the hardware-in-the-loop testing, and then minimize the real testing time during the certification. Then the test setup is represented in this slide, and we have three main components: a power system model, which is fully simulated by a dedicated hardware that runs the system in real time, providing results in real time. And we have we can represent up to 2 power store inverters with a detailed model of each component, and then we use to add also a virtual model of a point of connection to a grid, where we are able to control voltage, the amplitude of the voltage and the frequency, and also the strength of the grid, in order to test as many conditions as possible. And typically we add also a breaker in order to simulate connections and disconnections from that grid. We then have some loads that have a controlled profile so that we can regulate them based on the needs of our test. We then have the controllers in the loop part with a dedicated hardware that includes 2 control units of our 2 virtual power stores, and there we are free to upload any firmware version that we need to test and rapidly start testing it. The interfacing is made through to the simulated part is made through analog and digital signals. And then we have the monitoring and control interfaces that allow us to create events in the simulated environment and to control our inverter through sending to the possibility of sending command and receiving feedbacks from the inverters. And now we have the system testing, which is like an evolution of the unit testing, because compared to the unit testing, we have some additional control layers. Indeed, we have the image control added to the test setup. So we have, in this specific case, we have a distributed control with several controllers that each of them takes care of one of the DER in the simulated model, and are all interconnected with each other. And then we also add the image SCADA. With this test setup, we are then able to verify the coordination of our control logics that are running on different hardware and also at a different speed. We can also verify the power management made by the image control, and also we are capable of testing and verifying the communications between all these control systems, because in a system like this with distributed controllers, also the communications play a key role. On top of that, we are also able to check the utilization of all the controllers, so all the processing units in our controllers, in order to make sure that we utilize them until a maximum value in order to avoid problems during the operation. And then one last important application of a test setup like this is the possibility to simulate digital twins of our customers' plants, because even though this is a deeply tested solution, we from time to time we can have problems reported from site. And in that case, we are able to easily port the configurations from site and basically load the configurations from site on our test setup in our lab, and quickly start replicating the customer plant and try to find any possible or at least start to try to address the problem that was reported. And also this solution is definitely very effective. Then so far we have seen how hardware in the loop, the hardware in the loop technology allows us to, let's say, it opens the door to a multitude of testing possibility. But we also have to to maintain the efficiency of our testing process. And we some key points for an efficient testing process, in our opinion, is first of all, we have to acknowledge that testing consumes a big portion of our development time. It's not just a marginal activity. Then all the tests that we run with this technology have to be repeatable, and very often we need them to be repeated by different users. And this should not affect the final result of the test. We then have some tests that serve just as regular sanity checks, meaning that we run them very often, just to make sure, for example, that logic we have developed recently has not been affected something that was already working in the past. And then we have some other tests that instead are to be run on events. For example, before releasing a new version of our control solution, we used to do some deep testing on it. Then most of the time, a test has to be iterated because, for example, we need to find the right tuning for our controllers, but also because there are some cases that, for example, if we consider a fault right-through capability test, we typically have to test many different types of faults with different durations. Therefore, we end up with a high number of iterations of tests with very similar conditions and always with the same procedure. Last but not less important is that processing and saving the test results requires time and people. And sometimes we do that just in order to, as I said before, verify that, let's say, just to do a regression test. So to verify that our solution is still working as it was working in the past. So manual testing is not a practical solution for this. Therefore, we have switched to using automated testing. With automated testing, we can basically break down our test procedure in a list of commands that we collect in a script. And then this script can be run and iterated as many times as we need. So we can have an automation platform just to run the test at the cadence we want them to run. And we are sure that every time we repeat that test script, it will always behave the same way as it was behaving in the past. Then we have we use PyTest for this testing solution, and it is a well-integrated solution, so we can take advantage of that. Let's say we can add also pass and fail conditions and create test reports in order to minimize the processing time. And with a good parameterization, we can also reutilize many scripts in order to apply them to all the test cases we need to cover. But so let's say I hope that with this short presentation, I've been able to convey the message that hardware-in-the-loop testing has become a pillar in our development. And I will now let Henrique to continue on this topic.
Thank you, Michele, for starting the presentation and everyone that's attending the conference. To continue this topic, I'll be expanding a bit more on the test automation for the integration process, from developing the firmware until the system integration. My name is Henrique Magnano. I'm a Polytronics and HIL Test Engineer at Typhoon HIL. A key point for streamlining this integration is using test automation. So we will start by going over the reasons why you should automate your tests. Being able to test early in the development process, use a test-driven approach, and validate each step can prevent huge project refactoring. The good news is that we can use HIL Test automation to improve this development integration process without disrupting ones that are already in place. Hardware-in-the-loop is a great tool for development, maintenance, and integration. It has already proven itself as a cost-effective methodology and increasing product quality. As we know, when using hardware-in-the-loop, we can eliminate the power stage, creating the safe and easy environment for developing, testing, and validating. We can go a step further and now run unsupervised tests at any time throughout the project. By implementing test automation, you can achieve repeatable, scalable, and reusable tests. By repeatable, we mean being able to run the exact same test over and over again. This allows you to quickly check all the functionalities for any implemented change, revealing unexpected effects of this update. By scalable, you can start automating your tests from day one. You can start by testing your modulation, the current loops, voltage loops, protection, all the way to power loops, grid support functionalities, and grid codes. By reusable, we mean that after having the first test in place, where you figure out the communication, the commands, the reporting, adding new ones is much faster. You can also use test automation to run hard-in-the-loop pre-certification tests for standards. This way you can very inexpensively fix issues before sending the product for certification. The standards are constantly evolving and changing. So if you have the tests for the previous version of this standard, you can very easily update the test scripts and check your product against it. For the daily verification and new releases, so having end-to-end test automation where every change will trigger tests and generate results will significantly speed up the development process, also ensuring a tested firmware for release. You can also make these results visible, being updated in real time on a TV screen, so the whole team can track the progress and quickly act to fix any issues. Going to integrating the process from the original equipment manufacturer, OEM, development all the way into system integration. Being able to use the same tools both during development and integration with a high level of fidelity is extremely valuable, especially considering this can be done by different companies. This high level of fidelity can be achieved by using the actual controllers in the loop, interfacing through the simulation. This is the so-called cyber physical system. In order to easily do so, we need standard hardware, models, and validation process. Here we can see a basic flow from the development to the system integration. The OEM starts by packaging their controller with adequate signal levels and standard connections, so it can be easily added to an existing HIL test bed. This way, this device can be readily available, allowing the OEM and system integrator to use the same hardware, making the customer support much easier. The OEM would then build the HIL model of the power stage of their product and, of course, the product firmware. It would run through the test automation process, making sure that everything is working. Finally, this model would be packaged into a library that can be easily shared, containing all the I/O mapping for that specific HIL-compatible controller. Now the system integrator can add this library component to their system model alongside with the HIL-compatible device hardware and run all the integration tests they need. And this test may include other HIL-compatible devices, such as other inverters, genset controllers, relays, microgrid controllers, and so on. If they find any issues on either the model or the performance of the product, they can give this feedback to the OEM, which would improve the model firmware, run this the automated test verification and validation process again, and distributed this updated model and firmware with all their customers. This way, we are creating long-term value for all the development efforts. It's no longer just using the early stages of the project. So what should we be testing in this validation process? A good portion of this was already covered by Michele. I'll just emphasize some points. We have basically two types of tests, product and system level testing. On the product testing, this is where the OEM would make sure the product behaves as expected under a wide range of conditions. Here, you need to decouple the product testing from the system level testing. You cannot run in a reasonable amount of time all the possible test combinations because they do grow exponentially. but you can bring the relevant information or the requirements from the system level into your product testing. This is where we need good engineers that can connect these two realms, identifying that certain faults, loads, line impedances, or other DRs will affect the performance of your product. Here's also where you'd be using different test harnesses to test different products or test the same product under different applications. On the system level testing, this is where you'd validate the interaction between different DERs and the loads. You could be testing power sharing with different droop curves or different droop strategies, mixing grid forming and grid following, testing the synchronization of all the DERs, how it behaves under faults, and testing black start, for example. The communication could be basically testing if the configuration is correct, sending commands back and forth, or you could be testing the effect of the communication latency on the dynamic response of the system, cybersecurity, or different communication technologies. On the optimization, you could run any number of scenarios in order to, for example, reduce the diesel consumption of a genset while islanded, properly do peak shaving, frequency support, increase the profits on a dynamic market. This is also where you could be testing different AIs for all these cases and compare the results. For both types of testing, product and system level, you can improve them by making your tests more generic and parameterizing them instead of creating thousands of tests. Make it agnostic to the device and the environment, the hardware in the loop or the lab, so you can easily change the device under test or the environment without modifying the test itself. Using the specification to create nominal tests and enhance it over time with edge cases or field data like grid impedance, transition faults, and different DRs and loads. We do see this integration and validation piece as a key point to building a resilient grid. So very briefly, here are some of the things we have been developing and are actively working on. Here's an overview of a typical workflow for development and tools used for test automation. We have the development and test teams receiving the requirements and the specification, interfacing with cloud-based tools for project management, code tracking, continuous integration, reports. That's going to trigger the test execution on a test rack with the test server, several HILs, real controllers, and visualizing the results in real time. In order to make it possible and more efficient, we have some tools and concepts. The HIL compatible concept, the OEM and the system integrator can use the same hardware and models, continuously improving them. This will greatly speed up building the system level models with real controllers and facilitate customer support and maintenance from the OEM side. Virtual models of DERs, when a specific DER or component of the system is not the main component to be evaluated, it is possible to replace it by its modeled version, where we capture the behavior of the real controller. This allows building bigger systems without adding more hardware components. The Typhoon test, this is our test framework. It is based on PyTest. That is an open source Python test framework. Typhoon test, it has automatic report generation that's quite flexible. It has a set of useful functions for interfacing with the HIL to do signal conditioning, signal analysis. It can be also used for applications outside of power electronics, and very easy integration with continuous integration and development tools. The dashboard, in summary, it's a tool that displays in real time the test results from Typhoon test and allows for a quick search of these test results. The test server, it's a turnkey solution that comprises the hardware and services to implement end-to-end test automation. This was a brief overview of the test automation and integration that will hopefully open the floor for any questions you may have. Thank you.